Hello everyone, I'm gonna talk about our work, the scalable C-phase cell library synthesis, with a DRC-aware lookup table to optimize valid PNSs. This work is about how to synthesize a C-phase cell library while considering the PNSs build each issue during the blood level PNR. We use a native DRC-aware lookup table to optimize the PNSs ability. This is today's outline. I will give a brief overview of the C-phase data structure to provide everyone with a simple understanding of its challenges and benefits, and the contribution and the motivation behind our PNS ability estimation model, and the methodology we use to implement it step by step. And I will go through the experimental result to show our improvement and give a brief conclusion. Let's start from the C-phase data structure. In left-hand side, it's traditional cell layout. So P and N type are separated, which means we have a much bigger cell area. And if we want to connect the P type and N type, we need to use a vertical wire. And in the C-phase data structure, the cell area is smaller than the traditional one. And the most tricky part is we can shift the position of the N-type and P-type device, make it possible to only use the horizontal wire to connect different devices. So the benefit will be a smaller cell area and a more flexible horizontal layer or N0 layer or N2 layer. And challenges are with a smaller cell area, the number of routing track is also reduced, which makes it more difficult to complete the cell routing or the routing in the block level. To solve these two challenges, we may require a more comprehensive routing engine and more comprehensive DRC model in the cell synthesis stage. Okay, this is our contribution. We propose a balanced DRC-aware RPA optimization scheme. The balanced optimization scheme makes it possible to optimize every I/O pin evenly without favor one of them. And we use the DRC model to predict the potential DRC caused by the excited blockage. And finally, we can achieve a speed improvement of 100 times compared to the state-of-the-art, and we still maintain or surpass the quality of the generated cells, which enable us to synthesize the high-driving strength cells, which are not proposed by the state-of-the-art, and we also can have some complex cell designs like multi-bit flip-flop. And in the block level analysis, we achieve a 99% DRC decreases compared with the state-of-the-art. Let's start from the motivation. Okay, the remaining PNSs RPA was proposed by this paper, PNSs BLT driving cell layout redesign and placement optimization, and they use a statistic method to estimate the PNS ability of the pin. For example, these two pictures give a very simple example. They define the distance called a PID, pin interference distance, and if there are two pins within the PID, then the access point of these two pins cannot be connected simultaneously, because if we connect this access point from left side and right side, we connect to this access point, it will cause some maybe end of line rule or some space rule violation. And The possibility we choose this access point for this pin is its length, so it's 1/3. So the remaining of this access point will be 1 minus 1/3 will be 2/3. So the overall RPA value of this pin will be 7/3. By the same way, we can compute the RPA of this second situation, which these two pins share 3 tracks. So RPA value is 2 in this example, and which means if we use RPA to optimize the pin accessibility, we finally generate the cell layout like this. However, RPA model doesn't identify the invalid access point due to potential DRC. These green segments represent the excited metal tool. It may caused by the internal cell routing. So we cannot use metal tool to connect this point because it will cause the end of line violation. So these two are invalid. So the real DRPA is 2/3 for this pin in this example. And the second situation, the DRPA, the design aware remaining pin access is 4/3. So we should choose this. So this picture shows with the consideration to the potential DRC, the DRPA can have a better solution. Let's talk about the methodology we use to build our cell synthesis flow. Okay, we take the 2 stages flow to synthesize, and we optimize the cell area and some density criteria in the cell placement stage. And in the cell routing stage, we design the position, the shift position, or the contact allocation by the router, which we use an SNT-based solver to implement and optimize the routability and pin accessibility in the routing part. Okay, let's talk about one of the important contributions to make it possible to optimize the RPA by SNT solver. We use a lookup table to store the RPA value of the pin situation. Okay, instead of just compute the overall RPA of a pin, we decompose the RPA of a pin into its access point. So it will be 4 access points for this pin, and then after computing each access point, we sum up it, and this value represents the final RPA of this pin. If we want to compute the RPA of this access point, we need to check the neighbor, the left side neighbor, and the right side neighbor. We encode the neighbor into a binary vector. For example, this neighbor is length of 0, so it will be encoded by 1, 0, 0, 0, 0. And this point will be encoded by 0, 0, 0, 0, 1 because its length equal to 4. Then we sum up these two vectors. We will generate this vector represent the RPA key of this access point. By the same way, we can encode this access point. The left neighbor with length 3 and the right neighbor with length 4. So the final encoded value vector will be 0, 0, 0, 1, 1 for access point B. And because we define the space and PID, so we can only consider the left side and right side neighbor, the first left side and first right side neighbor. So the possible combination of this vector will be equal to this function, the t squared. And we already know how to compute the RPA for this situation, right? So we can store this value into the lookup table. But instead of storing the floating point, we scale it to integer, make it possible to optimize in the integer mode and speed up. If we use 4 tracks, then the scalar will be 12. If we use 3 tracks, the scalar will be 6. Okay. And let's go to the DRC aware RPA. First, with a solver-based engine, we will set several DRC constraints, and with this DRC constraint, the solver will give us a DRC-free result. And by using the same idea, we can create an other variable set called a simulating space. So simulating space is basically another variable set. It's like grid variable or something to define the connection between the grid, connection of metal or something. And then we also apply the DRC constraint to the simulation space. Then we can try to simulate the PSS process in the simulation space. Then DRC constraint will automatically force it to achieve the valid solution. For example, if we want to check if this point is valid or invalid, we can create a variable in the simulation space here. And because DRC rule will force it to satisfy the minimum area rule, it may extend to right. And when it extends to right side, maybe it will trigger another rule again, so it will enumerate. And while in the final stage, it may detect it finally cause the end of line, and there is no solution for us to access to this access point. So this is not a valid, it is an invalid access point. So this is a valid example. We create a variable in simulating space, and it will extend automatically and finally find one solution. So this is valid. If this is valid, then the DRPA value is equal to the RPA value. This is good. But if this is invalid, then DRPA is 0. Okay. Let's talk about the optimization scheme to ensure each I/O pin are optimized evenly. We propose a balanced DRPA scheme. So we first define a DRPA indicator to speed up the optimization. For each I/O pin, we want its DRPA value larger than a given threshold. This threshold could be any value. Well, we set it by the track number. For example, we want to measure this pin has at least one track is free. So we will set the one track, then we want to optimize for 2 track and 3 track, and we use the scalar value, so it will be 12 and 48. So we can incrementally optimize the DRPA value to measure they are optimized evenly. And one simple implementation method is we can after we finish one iteration of the 12 and we give a value, maybe this value is equal to 3, which means we have 3 IO and have DRPA larger than 12, right? So we can set this a new hard constraint and to optimize the 24, and finally we can get a solution that IO pins are well optimized evenly. Okay, let's go through the experimental result. These are the cell type. For N-type family, we use 3 different N cell, and these are the cell area, the metal track we occupy, the number of N2 track we occupy, and the total runtime and speed up. And the result shows we can achieve the same quality or much better quality. And the total runtime is shorter. The speed up can achieve 1,000 of speed up. And we can also synthesize a hydrogen strength standard cell and a multi-bit flip-flop, which are not proposed by the state-of-the-art. And finally, in the block level analysis, we can achieve 99% DRC reductions. Okay. The conclusion is we demonstrate that our synthesis methodology is highly scalable, and we can have the same quality or even better quality compared with the state-of-the-art. And our proposed DRC-aware RPM method can help us achieve 99% reduction in DRC violation in PNR stage. Thank you.